Well, circular motion problems come up in all shapes and sizes, so let's have a look at a few different situations. The first thing to realise is that there's a kind of basic principle to be followed, and that is this, that if something is going in a circle, then there must be a physical force or a combination of forces acting on it towards the centre of the circle, because something or a combination of things is making it go in that circle. And we know that when something's going in a circle, there's a resultant force towards the centre of the circle called the centripetal force. So really, really important. And so let's write here, that's the centripetal force. So, and we know, of course, that the centripetal force that is making it go in a circle is also equal to mv squared over r. So very useful fact, and it's to find out what's providing that centripetal force which is so important. Well, there's two steps to follow really to get started so in any problem. So the first step is to label all the forces. So if you've got a problem or question, something's going in a circle, label on the real forces which are acting on it. So whether it's gravitational force like the weight, or a tension, or a magnetic force, whatever it is, label all the forces on the body which is going in a circle. And then secondly, decide which ones of those are providing the centripetal force. Which ones of those, in other words, have a component, or they might be complete in their direction towards the centre of the circle, or have a component towards the centre of the circle. So, so those are the two steps to follow to get started at least. So let's try one. Let's do an example of a horizontal circle first. So horizontal circles, a ball on a string at 35 degrees to the vertical is making a horizontal circle of radius 0.4 meters, find its orbital speed. So the first thing to do then, of course, is to draw a diagram of that. So, well, when it talks about this kind of horizontal ball on a string thing, then what we're really saying is one of these kind of, you know, like a hypnotist's ball on a string, like a pendulum, but not going backwards and forwards, but instead kind of doing kind of circular rotations. Its official name is a conical pendulum. Well, it says in the question that it's making an angle of 35 degrees to the vertical. Great, so we've got our diagram. So what do we have to do? Well, we have to do step one. We've got to label on all the forces which are acting on the thing, the body, in this case this ball, on a string, which is going in the circle. So, well, obviously there's the tension in the string, so that's the first one to label. I'm going to call that T. And the only other force acting on there, on this body, is the weight. So I shall put that acting as the weight always does, straight down. There it is. And let's just call that for now mg. Well, we know there's nothing else, so between them those forces must be making it go in the circle, and that's our step two, isn't it? We've got to decide what is providing the centripetal force. Well, it's clear that the mg, the weight, is not going to have anything to do with the horizontal circle because it's purely vertical. So we can basically ignore the weight in terms of the circular motion. T does have a component towards the centre of the circle, and we can see that it's the horizontal component of T which is providing the centripetal force. So we've come quite a long way. We now know what is making it go in the circle, what is the resultant force acting towards the centre of the circle, and so we can set that equals to mv squared over r. So let's have a go at that. Well, the horizontal component of T, well, clearly this angle is also 35 degrees here. So the horizontal component of T, let's call that TH for T horizontal, is going to be, in this case, T sine 35. And that's going to equal mv squared over r because it's providing the centripetal force. So we've done pretty well. We found an equation, we found some useful information there. Well, to go a bit further, we've been asked to find its orbital speed, and at the moment, Well, we've got an equation with radius we know, mass we've got no idea, t we've got no idea, so it looks like, we haven't got enough information. Let's look what else we can deduce. Well, we know that vertically the ball is not moving. Vertically it's at rest. It's not moving up or down. It's not accelerating up or down. It's not moving. It's not moving at constant velocity up or down. It's just stationary. And the forces are therefore balanced. Well, they would be balanced, wouldn't they, if it was moving at constant velocity up or down? But the forces are balanced vertically. So we can write down, therefore, that the vertical component of t is equal to the weight. And that is t cosine 35, as we can see, which equals mg. So we've found ourselves another nice equation, and now we can do a bit of work eliminating things and see what comes out. Well, mathematicians would have spotted a sneaky thing we can do. Very, very nice tip for these kind of questions is to divide the equations. If I divide the top equation by the bottom equation, then, well, dividing the left-hand sides gives us t sine 35 over t cosine 35, and dividing the right-hand sides gives us mv squared over r divided by mg. And of course the t's cancel, and sine theta over cosine theta is tan theta, so it's looking good. So we can write down that tan 35 equals mv squared over mrg. If you want to pause to make sure that you agree, go ahead. M's cancel out, and we end up with a rather interesting and simple equation. That if we rearrange, we get that the square of the orbital speed is the square root of rg times tan 35. And of course we know r is, they give us in the question, r is 0.4 meters, g of course is 9.81 meters per second squared. So we can evaluate v. And if you want to pause and see what you get, you should get v equals 1.66 meters per second. So there we do. We've got the orbital speed from a nice mathematical approach to a horizontal circle.